So today we're going to be looking at some word problems as well as something called population density problems. Population density problems usually will end up in your multiple choice question, but the word problem that we're going to do is an example of a free response question from AP. And so we're going to be looking at how to sort of tackle these questions and making sure you're picking out the right parts of the problem. So our example is Rochelle rode a stationary bicycle. The number of rotations per minute at time t is modeled by a differentiable function r. So this is important. Okay. And values for r for select values of t are shown below. So it's important to notice that r of t is rotations per minute here. Okay. So if I want to find r prime t would be your change in r over your change in t, or rotations per minute. It's like your acceleration of r, right? So r is already a rate of change. R is rotations per minute. So r prime would be rotations per minute, or rotations per minute squared, which would be an acceleration, okay? So right now we're seeing that you're speeding up as you approach your time is 5 and then slowing down again as you approach time is 9. So probably what's happening is you're starting to pedal faster and faster, and then maybe you get tired and so you slow down. So it's telling us to estimate, and that's because we don't know what r of t is when t is 4. We also don't have a function to use to just find a derivative. So our estimate would have to be our change in r somewhere around 4. So I'm actually going to change this t to a 4 because it's straight there. So r prime of 4, we'd be looking for our change in r over our change in t. And so I'm looking for t values near 4. So I'm probably wanting to know what's happening from 3 to 5, and that's going to give us a good estimate of our acceleration at 4. So this means that on the bottom, my delta t would be 5 minus 3. On the top, I would have r of 5, not f. So used to using f. R of 5 minus r of 3. So r of 5 is 112, r of 3 is 95, 5 minus 3 is 2. This gives us 17 over 2, or 8.5. And then the question is, indicate units of measure. Well, the top has a units of measure of rotations per minute, and the bottom has a measure of minutes. So this is rotations per minute, or 8.5 rotations per minutes squared. Either one of those. Okay. The next question is asking us, is there a time t between 3 and 5 where our r would have to reach 106? And so if I think about this logically again, if I'm moving from t is 3 to 5 and my rotations are increasing from 95 to 112, if this is a continuous function, I have to reach 106 rotations per minute somewhere between 3 and 5, right? So the question is one, why am I allowed to do that? And two, how do I know that this is continuous? Well, I know that this is differentiable. It tells me in the question that r is differentiable. So if it's differentiable, it must be continuous. So we know r is differentiable on 3 to 5 because the question says it's actually differentiable from 0 to 9. So therefore, r is continuous on 3 to 5. So if I think about this logically, again, if it's continuous, it must reach every value between 95 and 112, right? We can't be skipping from 95 to 112, or else there would be some sort of jump. We would not be continuous from 3 to 5. So if I am continuous, I know that r of 3 is 95 and r of 5 is 112. And I know that 106 is between these values. And so therefore I know that I must pass 106. And there's a theorem that lets us say that. So we can say by intermediate value theorem, there exists a t in the interval 3 to 5 such that r of t is equal to 106. Okay, and this is rotations per minute. So again, you'd be able to determine that logically, if this is continuous, I have to pass 106 somewhere between 3 and 5 because I've got a number below 106 and above 106. But that's not going to be sufficient for them on your AP exam. You would need to state why you're allowed to say that, and that's intermediate value theorem. So you do need to make sure that you know all of your theorems. So squeeze theorem, mean value theorem, intermediate value theorem. You need to know definitions of things like a critical number, all those sorts of things. So please make sure you go back through and review your theorems if you have not. You will need those for your exam. Okay, the next one's asking us to use a left Riemann sum with 4 subintervals indicated by the data on the table to approximate the integral of r of t dt. So we know that if I do an integral, my r of t is rotations per minute, dt or delta t, depending on how we want to think of this, is minutes. And so my integral, my units are rotations. Okay, so it's asking us to use correct units. So I'm looking, really what I'm looking for is I'm looking for the number of rotations completed from 0 to 9. Okay. So I also know, since I'm using a left Riemann sum, I know that when I use a Riemann sum, I'm looking for areas of rectangles, and my area of each rectangle is delta x times f of xi. So the question here is, well, what are my f of xi's? Well, basically, if I split this into 4 subintervals, I've got one from 0 to 3, I've got one from 3 to 5, one from 5 to 6, and one from 6 to 9. And since I'm using a left endpoint, for my first one, my left endpoint here would be 0, which is my x1. My left endpoint of my next rectangle would be 3, so that's going to be my x2. My third rectangle, my left endpoint is 5, and my last rectangle, my left endpoint is 6. So what this means is my total rotations is equal to the integral from 0 to 9 of r of t dt, or using a Riemann sum with a finite number of subintervals, this is going to be delta x times f of x1 plus delta x times f of x2 plus delta x times f of x3 plus delta x times f of x4. And we know x1 is 0. And our first rectangle would go from 0 to 3. So our delta x or delta t would be 3. F of x1 or f of t1 would be f of 0 or r of 0, which is 72. Our delta x for our second rectangle was from 3 to 5. So our delta x is 2. And our f of x2 would be f of 3, which is 95. Our third rectangle goes from 5 to 6, so our delta x is 1, f of 5 is 112, and our last rectangle goes from 6 to 9, our delta x is 3, and f of 6 is 77. And in total, this is going to give us 749, and our units is rotations. So if I explain the meaning of this, this is going to be 749 rotations in 9 minutes. So on AP, usually what will happen is you'll get a bunch of marks for the math here, and then they'll give you something like 2 marks total for all of your units being correct or something like that in the entire problem. Okay, last one is saying Sarah also rode a stationary bicycle. And again, she's got a number of rotations per minute. Okay, so S is in units per minute. This is a rate. Okay. And it's wanting us to find the average number of rotations per minute. So we know that her total number of rotations in 9 minutes would be the integral from 0 to 9 of S of t dt. To find the average, we would then need to divide this by the total number of minutes. So our average number of rotations is going to be 1 over 9 minus 0 times the integral. And that's from our average value of a function. We know this. Now the problem is that our function here is quite gross, and so I probably want to use my calculator for this. So to find my integral, I'm going to use my calculator and then figure out what this is. So if I pull out my TI-83 calculator here, it's doing some weird things, but we'll figure it out. We're going to go under math. Oh, I think it turned itself off. So I'm going to go under math, and then I'm going to go under integral. And a reminder that then you're going to put in your function. So for us, it's 40 plus 20 pi. And I've got a pi around here somewhere. Where's my pi is up here under the clear button using second. So I'd go second and then the little hat looking thing, 20 pi, and times sine of pi t. They don't have a t, it's just all on this one button. It's going to come up as an x over 18. Close the bracket for sine, comma, our variable, comma, our lower bound 0, comma, upper bound 9, close bracket, enter. It's going to think, and it tells us it's 720. So I'm going to use my calculator. Okay. So if I use my calculator, I'm going to go math, then down to fn int. And then you're going to input function, comma x, comma 0, comma 9, and then hit enter. Okay, and this was okay. So once I do that, I'm going to get 80. And because the 70 or 720, the units of this is rotations. And this is a units of minutes on the bottom here. This is 80 rotations per minute. So the last part of today is going to be looking at population density. So population density, when you're thinking about density, you're thinking about how many units are in a certain area usually. So for example, for a materials density, it's mass per unit volume. The questions that AP likes to give you is population density. So you can think about this as people per mile along the edge of a city, or if you're thinking inside of an entire city or something like a field or a building, you're usually thinking about the number of people per square mile or per square area of some sort. Okay. So usually when we think about cities, you think about having more people near the center of the city compared to less people on the outside. And if you're comparing a specific area, that means the density in the center is, for example, per square mile, the density in the center would be higher and the density near the outside would be less. So when we're thinking about these, we're going to think about these as still um, adding up a bunch of rectangles or circles or whatever. And inside each rectangle or circle, you basically have a bunch of people. Okay? So, for example, we've got a city located beside a river, and the city has this rectangular bound as shown. And so, if I wanted to think about um, the fact that the population density of the city at any point from the river's edge is f of x person per square mile. So it's saying at any point from the river's edge, x miles from the river's edge. So you might have people here, okay, or you might have people closer to the river. Okay, and this distance here would be x miles from the river's edge. So if I think about one of these strips, the area, well, this x and this x would be different. And your distance at the bottom of that rectangle would be some delta x value, and the height of the rectangle would be 7. Okay. The area of this strip, well, both those units are miles. So the area of one strip is in miles squared. Now, f of x is our density, and the units of this is people per miles squared. So if I wanted to find the number of people in this total area, right, the number of people in just one strip would be area of the strip times f of x, or the density of that strip times the area of that strip to figure out how many people there are total. Okay. So the number of people in one strip would be the area times f of x. Or for us, the area of one strip is 7 delta x, length times width. And this would be times f of x, whatever our f of x may be, which means our total area, our total number of people would be adding all these strips together. And remember, one way to do that is an integral. So if I integrate 7 delta x f of x, that's going to give us our total area. Now the question is, well, what are our bounds? The city does stop. It doesn't go on forever. And our first x possible that we would have would be 0 miles from the river's edge. And our last possible x we would have would be 4 miles from the river's edge, which means that our total number is going to be from 0 to 4. And I'm going to rewrite this as 7f of x. And instead of delta x, I'm going to write x. And this would be the total number of people in our city. Because from 0 to 4, you would be adding together strips from a distance of 0 miles from the river's edge all the way up to a distance of 4 miles from the river's edge. So the next one we're going to try is a little bit harder, and it's saying you've got a city built around a circular lake. So here's my lake. Oh, let's try that again. Here's my lake. Okay. And it says that the lake has a radius of 1 mile. Okay. Now it's saying the population density, again, F of R is people per square mile. Okay. And R is the distance from center of the lake in miles. And it's asking for people who live within 1 mile of the lake. So this city goes outwards only until you are 1 mile from the lake. So when we think about where you're going to put the areas, it's the closest you are to the center, you're going to be the most dense. And as you go farther and farther outwards, your density will change. And so basically, you're looking for, if I had circles that I'm going to add up together. Okay. So one of these circles is what we're trying to add up. So if I change this so that this becomes a strip, right? The distance from the center of the lake out to the outside would be some distance r. Okay. And the thickness of this between this r and the next circle outwards would be delta r. And if I expand this circle out to be a rectangle, then this length is my circumference, which is 2 pi r. So the number of people in one strip is going to be, again, my density of my strip, f of r, times my area of my strip, or f of r times 2 pi r times delta r. And that's because the area of a strip has units of miles squared. So to find the number of people in a strip, we would take f of r and times it by the area. So in one strip, we have f of r times 2 pi r times delta r. And so the total number of people would be adding all this up. I'm going to change my delta r to a dr. And now the problem is what are our bounds going to be? Well, we don't start from 0 because we're not filling people up in the middle of the lake, right? The smallest radius that we are going to have of one of our strips is at the edge of the lake with a radius of 1. And because our total distance from the middle of the lake to the outside of the city is 2 miles, we're going to keep going up till 2 miles. So we're not filling in the blue spot in the middle because that's our lake. We're basically trying to fill in from the lake outwards. We're trying to fill in this whole area here with people all around the outside. And we don't see this answer here because there's a 2 pi out front of everything. But if I take my 2 pi out, then I get r times f of r dr, which is so again, I know I'm not putting people in the middle of the lake from 0 to 2. And last one here. So another word problem for us. Okay, so suppose that the current model, or the current world population is 7 billion people, and the population t years from now can be modeled by this p of t. And it's saying use this information, what will be the approximate average population in billions over the next 15 years? So population t years from now is our p of t. Okay. So if we want to find an average, we know that p average, trouble with my touch screen today, is going to be 1 over 15 minus 0, because we're going from now until 15 years from now. And then our integral would be from 0 to 15, p of t dt. And this equation is going to give us 1 over 15, integral from 0 to 15, of 7e to the 0.02t dt. And again, we could try and do this using chain rule in our head, but you can also use your graphing calculator. So again, if I use my calculator, I'm going to go here. I'm going to use my math button. Oh, let's turn it back on. I'm going to use my math button. Go down to integral, enter this equation, which is 7 times e. E is down here by the ln, to the 0.02t, or x, close my bracket, using the variable x, I'm going from 0 to 15, enter, and I get 122.45. And if I do that, I get 8.16 billion. So again, there's some board questions that you can try for practice, and I've added some sample AP problems as well.